and welcome to Calculus Fun with Mindy. I'm Mindy, and today we're going to talk about Rogowski Calculus Chapter 3.10, which is implicit differentiation. We're going to talk about what implicit is, how we solve these problems, and we're going to do that through some examples because I think that's the best way to learn it. So if you look here, we have an explicit function, which means we have y's on one side and x's on the other. And this is what you've been working with for the past few weeks now. So if we go to take our derivative, we see that we get 2x minus 1 over x squared. Now, if we want to find the equation of the tangent line, we simply plug in our x value to get m. So in this case, m is 1. Then we use our values, so y equals 2, m equals 1, x also equals 1, to solve for b. So b equals 1 as well. And we find the equation of this tangent line is y equals x plus 1, which makes sense given the line that we're talking about here. Okay, with an implicit function, things are a little more complicated because we have x's and y's on the same side, and they cannot easily be separated from each other to make a nice function. So what we do is we take the derivative of each side separately, and we can still split up the derivative at addition and subtraction, just like we always have. So we get the derivative of each piece So the derivative of of x squared is fairly straightforward. We know that that's 2x. Now this derivative is more complicated because we encounter our first y. But what we do is we treat y like a function of x, and then we will need the product rule in order to take this derivative. So we take the derivative of x, which is 1, and then we leave the y alone, plus we leave x alone, and we represent the derivative of y by writing dy dx. This shows that a derivative was taken with respect to x of the function y. So when we do this one, we get 2y dy dx, and that's just like the chain rule. We brought the power down, rewrote the inside, and multiplied by the derivative of the inside. And of course, the derivative of a constant is still 0 here in implicit land. So we're going to take this, and now we're going to want to solve for dy dx like we had in the other one. So we rewrite and distribute the negative. We get this is equal to 0. Now, in order to solve for dy dx, we want to move all the non-dy dx terms to the other side. So we'll subtract 2x and add y, which gives us negative x dy dx plus 2y dy dx is equal to negative 2x plus y. Now we can factor out the dy dx on this side since both terms have it in common. So we'll get dy dx times the quantity negative x plus 2y is equal to negative 2x plus y. Now you may have guessed our next step is going to be to divide by this quantity to get dy dx by itself. So dy dx equals negative 2x plus y over negative x plus 2y. So we are back to kind of the same setup that we had before, and we're going to have to plug in our x and y values this time since we have functions of both y and x. So m is going to be negative 2 times our x value, which is 3, plus our y value, which is 2, over negative 3 plus 2 times 2, which is going to give us negative 4 over 1. So that makes sense with our function here, which we can see is pretty steep and in the negative direction. So again, we know y is 2, m is negative 4, our x value is 3 plus b, so we get negative 12 here. So we'll add 12 to both sides, which gives us that b is 14. So we know that the slope of this tangent line, or the equation of that tangent line, is y equals negative 4x plus 14. Okay, this is a pretty straightforward example of implicit differentiation. So let's look at something a little bit more complicated. As you can see, we have a quotient in this one, which makes things a little more complicated if we use the quotient rule. However, implicit differentiation says we're going to take the derivative of both sides anyways. So let's lighten our load a little. If we multiply both sides by x minus 2, we can simplify this a little bit. So we'll get x squared y minus 2y cubed is equal to, and I'll distribute this 5x through, so we get 5x squared minus 10x. Now this looks quite a bit like our first example that we worked with, in that it's all on one line. So that will make our lives much easier. So now we'll take the derivative of both sides, with respect to x, of course, and we encounter another product rule here. So the derivative of x squared is 2x times y plus x squared times the derivative of y, which is dy dx. Minus, now we'll bring our power down, 6y squared times dy dx, to show that we took the derivative of y with respect to x. And this one is pretty normal, 10x minus 10. Now, as you recall, we want to get all non-dy dx terms to the other side, so we'll want to subtract 2xy from both sides. That means we have x squared dy dx minus 6y squared dy dx is equal to 10x minus 10 minus 2xy. Now, as before, we'll want to factor out dy dx so that we can divide by the remaining terms. So, dy dx times x squared minus 6y squared is equal to 10x minus 10 minus 2xy. And we'll divide. To get that dy dx is equal to 10x minus 10 minus 2xy over the quantity x squared minus 6y squared. There we are. Since we have no points to plug in for a tangent line, we simply leave it as this. Now, this is a pretty cool graph of this function here, which is an implicit trig function, which looks really big and scary. So let's try and work this through. We still start the same way, by taking the derivative of each side with respect to x. So we have another product rule. The derivative of x is 1 times cosine y plus, we leave the x alone, and the derivative of cosine y is going to be negative sine y. Equals, now we take the derivative of y, dy dx. We'll want to put the dy dx over here as well, since we took the derivative of a function with y in it. Dy dx sine x plus y cosine x. Okay, so now we have all our dy dx's in line, and we can start moving things around. So I'm going to add x sine y dy dx to both sides, because then I don't have to deal with negatives and gross stuff. So we'll subtract this y cosine y, or cosine x to the other side. And that'll give us, we will have 1 cosine y minus y cosine x is equal to sine x dy dx plus x sine y dy dx. So So, again, I sound like a broken record, but we want to factor out dy dx so that we can divide. So we leave cosine y minus y cosine x alone, and that's equal to dy dx times the quantity sine x plus x sine y. And our final step, as always, divide by this term. Which will give us our final result that dy dx is equal to cosine y minus y cosine x over the quantity sine x plus x sine y. Since we don't have a point to plug in for a tangent line, we're done. So until next time, thanks for watching.